So as we all know, so AdS-CFT is a duality that maps a quantum field theory, which does not have gravity, to a gravity theory. And of course, this is really the first example of such a particular duality, while there are many other dualities in quantum field theory. And so really this provides us with a new approach to quantum gravity. And so this is a really important step for many, many reasons. To remind you, the original motivation for this conjecture, so let's recall that AdS-CFT is still at the level of a conjecture. And the original motivation, strong motivation why this conjecture should be true comes from string theory, as proposed in the original paper by Maldacena already in 1997. And so the string theory motivation comes from considering the near horizon limit of D-branes. And I will review this very briefly to get everybody on the same page. Now, the original AdS-CFT correspondence, of course, has a number of crucial features that enter. First of all, there's a lot of symmetry, supersymmetry, and also conformal symmetry. And another important ingredient, of course, is the large n limit in the quantum field theory, which really amounts to a saddle point approximation, meaning that we look at Gaussian distributions in the quantum field theory. Okay, so let me very briefly review the string theory origin of AdS-CFT to highlight a few features that become relevant in the context of information geometry. It's a duality between open and closed strings. So here is our stacks of D-branes, D3-branes in the 9+1 dimensional background. And so there's a duality at the string level between open and closed strings. And so the ingenious idea of Maldacena was to propose a particular low energy limit, which really consists of two steps. The first step is that on this side here, we move to classical string theory by writing the string coupling as 't Hooft coupling divided by n, and then considering the limit where n goes to infinity while keeping this lambda fixed. So that brings us to classical string theory. And of course, to the large n limit in the theory associated to these open strings. And the second step in this limit is to take the 't Hooft coupling, which is given by the AdS radius to the 4th power divided by the string inverse string tension squared to be very large. And so that limit here on this side brings us to the limit of classical supergravity with point-like particles. And it also involves the near horizon limit, which takes us to AdS 5 times S5. And on this side, this limit takes us to nx24 SUN super Yang-Mills theory in 4 dimensions, with n being large and also the coupling being very large. So, but the important feature I would like to mention in this context for this talk is that through this construction on both sides of the duality, we really know the Lagrangian and the action. So here we have an action for nx24 super Yang-Mills, and here we have the action for a classical type 2B supergravity in 10 dimensions in this particular geometry. So it's really a duality at the dynamical level where there's two actions which are mapped to each other. And then more precisely, there is the field operator correspondence, meaning that if we could look at the generating functional for correlation functions of particular composite gauge invariant operators in the conformal field theory, then according to AdS-CFT, this is given by the generating functional on the supergravity side, which involves e to the minus the classical supergravity action. And the fields in this action at the boundary correspond to the sources of this generating functional. Now, in the context of what I'm going to say here is now what is important here again, that we see the saddle point approximation in action, because here really what we do on the gravity side is to expand about the solution of the equations of motion in the gravity theory. And so it's really, again, it's a Gaussian expansion in the context of a saddle point approximation. And so it's one of the virtues of the correspondence that this generating function, which is associated with a strongly coupled quantum field theory, nevertheless gives rise to this Gaussian behavior. And of course, the large N limit plays a crucial role in this. Okay, so now the motivation to look at information geometry is to ask the question, is this duality valid more generally? So as I showed you, starting from the D-branes gives this very concrete and very controlled realization of this new duality. But since we still don't really understand this origin of the duality at a kind of mathematical level, the question is very valid if there's a broader framework in which we can understand it. So this is, of course, this question has many aspects. So one is maybe we can find a kind of orthogonal approach to understanding the basics of this duality, orthogonal to really understanding quantum string theory, which is, of course, very hard to do. But also then if the duality is valid more generally, perhaps we can construct further examples of this duality involving other spaces, other symmetries, and so on. So this is really the motivation to look at this information geometry concepts. And of course, a super important ingredient in studying this question, so I should say this question has been studied quite a lot over the last 10 years already by many, many authors. And I think it really started, or the most important ingredient to get this started was this relation between information theory and ADS-CFT in general, which is related to the holographic entanglement entropy as proposed by Ryu and Takayanagi in 2006. So as they proposed, the leading term in the entanglement entropy of the quantum field theory should be given by the area of the minimal surface in the holographic dimensions. So here, if we have our two entangling regions A and B, then the area of the surface will give this leading term in the entanglement entropy. And actually, this proposal passed many, many non-trivial tests. And this really sparked this idea of using concepts from information theory to study the duality. So this was kind of the starting point. So, after that, many other information theoretical quantile concepts were studied in this context. So now today, I would like to briefly show you essentially 3 of them. And now, actually, it turned out that, of course, quantum information theory is something which arises from many body physics. And so generically, it talks about concepts related to finite dimensional Hilbert spaces, where, say, you have a collection of spins. So if you think of quantum computing, say you have 10 qubits, and then there's discussions about how to process them in very different scenarios. But of course, if we want to use this in this context I'm discussing here, where we want to use it in quantum field theory, these concepts have to be translated into infinite dimensional Hilbert spaces. And so before we can actually address the question which I mentioned just now, we first have to establish these concepts really in quantum field theory. And so there are many interesting tasks already associated to this task, to this idea. Okay, so what I would like to show you in the next half an hour is, first of all, give you a very brief definition of what information geometry is, and in this context, discuss in particular the so-called Fisher information metric. And then I will also talk about modular Hamiltonians and modular flows. So this is a concept which already originates from algebraic quantum field theory, but now plays a very important role, for instance, in this context of space-time reconstruction in the context of ADS-CFT. And finally, I will make a few remarks about computational complexity. So complexity is another idea from information theory that now plays a very important role in quantum field theory and ADS-CFT. Okay, so and the upshot, so once I reach my conclusion, will be the following. So there will be many, many nice examples where we have relations between quantum field theory on one side and geometry on the other. But in the light of my introduction, that we really want to understand ADS-CFT, what is really missing is how to incorporate the dynamics in this picture. So geometry, per definition, is not a dynamical theory. And so actually, so to take away my punchline at the end, so there's many beautiful things which I'm going to show to you. However, in view of making progress towards the goal I presented at the beginning, the question is really how are we going to incorporate the dynamics and how to establish dualities similar to ADS-CFT in a much more general context using this information theory ideas. And that's really the open question that remains. I should say that many people have already proposed ideas how to get the Einstein equations in this scenario, but I think this is an unanswered question. And so what I hope to achieve with this talk is now that you will say, oh, wow, this is super beautiful. And I would really like to study now this next step, which we need to make further progress towards understanding the ADS-CFT. All right, so this was a rather lengthy introduction, but now let me enter the details and tell you about these 3 points. But before I do that, I should quickly thank my collaborators because otherwise I'm going to forget. And of course, I owe a lot to them. So essentially, I'm going to tell you incorporate results of 4 papers. One which was really about information geometry and quantum field theory that I wrote last year together with Kevin Grosvenor and Bro Jefferson. Then earlier with Shuvik Banerjee and Devalyoti Saka, I looked at this Fisher metric already in ADS spaces. Then there's a recent paper on modular flow together with Pascal Fries, who is a PhD student in Würzburg, and Ignacio, who was also a student, is now a postdoc, and Christian, who was a master's student. And then finally, with 2 other students, Marius and Annalena, we studied complexity in conformal field theories, and so this will be my last example. So you can see my list of examples is a bit biased by my recent interests, but I think it still covers quite a lot of things that are going on generally right now. Okay, so now finally, so what is information geometry? Well, it's a particular branch of mathematics that uses differential geometry to study probability theory. So really, it's a merger of differential geometry and stochastics, if you want. And one of the key figures in this subject is Professor Shunichi Amari from Japan. And so there's a book by Amari and Nagaoka, which is kind of the foundations of this, or covers the foundations of this branch of mathematics. Okay, so central to this idea is now the concept of a statistical manifold. So this is a Riemannian manifold whose points correspond to probability distributions. Okay, so this is really important to understand. So the manifold is really spanned by the parameters of these probability distributions. So we have a space of probability distributions that are linked to each other by a collection of parameters. Okay, so the probability distribution P depends on some stochastic variable, but then also on a number of parameters that I call theta, and the vector just indicates that there can be several of them. And of course, this should be normalized to be 1 to be a probability distribution. And so now this differential geometry applies to the smooth manifold that is spanned by these coordinates theta. Now, it is possible to define a metric on the space, which is precisely this Fisher information metric. And so this is a metric on the space of probability distributions in the sense that I just introduced. So now using the definitions I just introduced, usually what is done in information geometry is to define a function gamma, which is referred to as the spectrum, and that's minus the logarithm of this function. Okay, and then there's a concept called the Fisher metric, which is basically the expectation value of 2 derivatives of this spectrum with respect to the various parameters in our distributions. And so we can abbreviate this as in this way. So the expectation value comes from the fact that there's a P here. Okay, so now in view of ADS-CFT, there's actually a very interesting observation that has been around for a long time before ADS-CFT even. So it's been around since the 70s, I think, already. So again, if we are in a saddle point approximation in quantum field theory and have Gaussian distributions, then obviously our Gaussian distribution is going to look like this. And then what happens is that this Fisher metric precisely gives us an anti-de Sitter space, okay? And especially here, the variance or standard deviation of the Gaussian will correspond to the radial coordinate of our anti-de Sitter space. So these x's here, these x bars are the position where this Gaussian is centered. So they give us the boundary coordinate of our anti-de Sitter space, and the radial coordinate actually is given by the standard deviation. Now, that's super nice in view of what I told you before. So I emphasized that ADS-CFT is valid for in the large n limit, where we have a saddle point approximation where we have a Gaussian. And now you already see in this information theory context that if you have such a Gaussian distribution in a natural way, you can associate an anti-de Sitter space to this. So that these results are, oops, sorry, can you still see? Hello? Can you still hear?
Yeah.
Okay. Yeah. Okay. By the way, actually, if somebody wants to ask a question, please interrupt me. I mean, maybe this is a good point to say.
I will.
Yeah.
Yeah, because, well, I imagine that you're going to tell us more about what's the interpretation of this ADS metric. But I mean, its appearance here, it has to do mostly with scaling properties of the probability distribution that you have, right? I mean, that's
yes, exactly. Well, okay, you're taking away my next.
Okay. Then I'll shut up and then I'll ask later.
Yeah. Okay, very good. Okay, absolutely right. Okay, so the punchline was that, wow, this is super beautiful. This gives somehow some probability interpretation of ADS-CFT. And then I have to say, but, okay, so, and this is exactly, okay, just what we wanted to say. Okay, so there's a number of caveats, and yeah. Sorry. So as Roberto was saying, of course, as I said, I mean, there's no dynamics. It just reflects the symmetries in some sense of the distribution. But things are even worse, okay? So, and actually the first people to study this in this ADS-CFT context were, I mean, I think it goes back basically to Jonathan Schock, who used to be a postdoc with us, but also in Santiago de Compostela. And so he's now a lecturer in Cape Town University. And so together with Jeff Murrigan and a student, they studied these things already a long time before everybody else. Okay, so actually, there are some issues, and so they're listed here. Okay, so so first of all, this relation is not unique. Okay, so infinitely many distributions give the same geometry, and so for example, both the one-dimensional Gaussian and also the Cauchy-Lorentz distribution, they give two-dimensional hyperbolic space. Okay, so the conclusion is that many statistical models lead to the same information geometry. Okay, so it's not bijective. Okay, so you can, to a probability distribution, you can associate a metric, but not the other way around. Okay, then about the symmetries. So as Roberto was just pointing out, so the Fisher metric inherits the symmetry of the statistical model, but in fact, it can have many more symmetries than originally present. Okay, so in this paper, actually, there's an example of a probability distribution that gives two-dimensional hyperbolic space, but has none of its symmetries. Okay, so, okay, just to put this into perspective, so what I just told you is a very beautiful observation, but there are lots of issues which one has to be aware of. Okay, this said, let me nevertheless show you a couple of examples where people have studied this. And so there was another paper rather early on by Blau, Lorraine, and Thompson. And So this is already a long time ago. And so this somehow passed a bit unnoticed, which I think is a pity because this is a very, very nice paper. Okay, so what they do is they consider SU2 Young-Mills instantons in 3+1 dimensions. And they use the Hitchin prescription, which says that the probability distribution is taken to be the Lagrangian density of the state. And so the probability distribution is essentially this. And so if they have an instanton solution, this is what they start with the instanton symbol, the center of the instanton, which is again will span the boundary coordinates, and lambda is the instanton size, the instantaneous radius, and in fact, this again gives an ADS metric with the radial coordinate given by the instanton radius. So, which I think is a very nice observation, and I think what at the time what they wanted to do is also not just obtain the ADS5, but also the S5. But this is a little more complicated, unfortunately. Okay, but
so Johanna, can I interrupt you for a second?
Yeah, sure.
So in in the past there was work relating also the instantons to ADS5, but I think it was through the modular space
yes, that's right.
metric. Is there a relation with this? Is it the same thing? Or?
Yeah, it's very much related. Yeah. This is okay. Yeah, it's the same idea, but I think these were the first people to mention this Fisher metric in this context. But okay, it's a realization of this what you were mentioning, this discussion of instanton and ADS-CFT and the modular space. Yeah, that's correct.
Thanks.
Okay, so as we recently checked in this paper with Kevin and Rowe, is that this also works for the scalar instantons in a very analogous fashion. Okay, so in this paper we essentially have a review and collection of many interesting facts about this Fisher metric, which we tried to put into perspective a little bit as a basis for further investigations. And so still with this caveat that, there's this non-uniqueness problem, nevertheless, I think there's a few interesting observations that can be made. So actually, this Fisher metric can either be defined for theory space and also for state space, by which I mean the following. So if a theory is spanned by, so the theory space is spanned by the renormalized couplings of a quantum field theory, which we investigated for the Ising model. I will show you a figure in a second. But then also many people already a long time ago have investigated the geometry of RG flows in this way. And then another possibility is to define this metric on state space. And so I already showed you the example of the instantons, but you can also do a similar analysis for coherent states, which I will show to you shortly. Let me very briefly mention that there's a paper by Heckman already in 2013, where he actually considered this in string theory and found a worldsheet action for the Fisher metric, then which is one of the proposals which already implies the Einstein equations. Although I think this is also at the level of a suggestion, but I think this is important to mention in this context here. But now let me move on to this theory space. Okay. So let's look at the Fisher metric for this two-dimensional Ising model. So I should say there's quite a lot of work on the Fisher metric in condensed matter physics and also in quantum field theory. There's a group of Wolfhard Janke, who used to be a professor in Leipzig, and also by Brian Dolan in Ireland. And okay, I should also mention this recent paper, which actually by Eric Tonley and his student Di Giulio, and which makes a very nice connection to the complexity that I'm going to talk about later. And so this is a very thorough study of various aspects I'm mentioning here. So I really recommend this also as a review. Anyway, so here's our two-dimensional Ising model with the partition function. And so it also has a Gaussian probability distribution, which comes just from the fact that you use the canonical ensemble here. And so as was found already a long time ago, then is that this Fisher metric will be given by a derivative with respect to these couplings, J and K, of the reduced free energy per site. And here I can show you a nice picture from our paper where the Ricci curvature for this two-dimensional Ising model is plotted as a function of the couplings J and K. And so this is a view of the top from just looking at the top of this graph. And what is found, but this was also known in condensed matter already before, is that the curvature of the Ricci scalar associated to this Fisher metric diverges at the phase transition. So the phase transition between the ferromagnetic and the disordered phase follows this line, and it's precisely along this line that the Ricci scalar associated to this Fisher metric diverges. And so this is actually a tool which is used a lot in condensed matter to diagnose phase transitions.
Sorry, Johanna, sorry to keep interrupting you.
Don't worry.
Is that the same statement as the fact that this metric, because it's a second derivative of the free energy, is actually just the matrix of susceptibilities?
Yes, of course.
Those diverge at the phase transition?
Yeah. Yeah, of course, you're absolutely right. I mean, this, I think maybe I say it on the next page. Yeah, okay. So, yeah, of course, it's related to the susceptibilities. You're absolutely right. But it's a nice kind of somewhat model-independent tool to investigate phase transitions. But of course, as you say, in this case, I mean, it's really much related to the susceptibility, which is the derivative of the specific heat. Okay, yeah, so in other coordinates where we set J, the coupling constant is equal to 1, then actually the metric component, which has the inverse temperatures here, is actually given by essentially 1 over the difference between the temperature and the critical temperature. And okay, so this may be written as an effective mass scale here. So, and now what is quite interesting is that this can actually be reproduced in quantum field theory. So as is well known, the critical two-dimensional Ising model corresponds to a free field theory of free fermions, which is written here. And essentially, this mass here then corresponds to this mass there. And so then there's a different definition of the Fisher metric in terms of quantum field theory, which is given here. And so now for the couplings inserting just precisely this mass again, then this is the expression that one gets with this action here. And then this metric element in the quantum field theory is given by this expression. And indeed, it also scales with a logarithm of 1 over m, precisely in the same way as is obtained in the lattice model. Okay, so I mean, of course, in some senses, this is just a rewriting, but it's nevertheless interesting that if the Fisher metric is defined in terms of quantum field theory variables, making use of the fact that this quantum field theory is equivalent to this lattice model at a critical point, the matrix elements of this metric actually look the same, have the same behavior. So I think this is an interesting observation, at least.
So maybe I can say or just comment something on along the lines of what David was saying. So I mean, the way that I understand it, Fisher information is the curvature of a relative entropy.
Yes.
Whereas what David was saying is the curvature of thermodynamical entropy. So in principle, Fisher information is more general, right? Because the thermodynamic entropy, we understand it in terms of as a relative entropy. So I think that's...
that's a very good remark. Yeah, okay. So here, of course, this is very typical to this particular example that we are studying here. Yeah, I agree.
Okay.
Yeah, thanks. Okay, so the other thing I wanted to present is the Fisher metric. So this was for a metric on theory space, where the coordinates are really the renormalized couplings of the quantum field theory. Now, the Fisher metric can also be defined for states. And so that's actually where the relative entropy, so this is what Roberto was alluding to, I think. In the context of information geometry, there's the concept of the so-called divergence. So, and this is defined to be a bifunctional of two probability distributions P and Q that measures the difference between these two distributions. And the relative entropy that Roberto was just mentioning is then defined in such a way. So the relative entropy of two different probability distributions P and Q. And from this relative entropy, we can again define a Fisher metric. Before I called these theta, now they call psi. Never mind. So these are like these theta I had before. And so taking the derivative of this relative entropy then gives a definition of the Fisher metric. So now there's another concept in quantum mechanics. Okay, so the Fisher metric really is a classical concept in some way. And there's also a quantum concept, which is the so-called Buell metric. And this is defined for quantum states given by a particular density matrix. So there's something called the Buell distance, which is defined in such a way. So this expression looks a bit unwieldy. So this is sometimes referred to as the fidelity also. But if you just insert a pure state, then this product actually reduces just to this scalar product here. And the Buell metric is then the leading quadratic term in the expansion of this divergence around the point where these two density matrices coincide. Okay, and so just very briefly, so this may now also be defined for coherent states. And so an interesting fact, so a coherent state is a state which is an eigenstate of an annihilation operator. And so this can be defined for fermionic and bosonic fields with a parameter lambda, which is a complex number essentially. And then it's found that for fermions, it looks like this. And for bosons, there's a minus sign here, and it appears in the numerator. And then again, calculating this Buell metric, then for the fermions gives this structure, and for the bosons, it gives that structure with a different sign. Okay, which is of course related to the usual sign in the Fermi-Dirac and Bose-Einstein statistics. Okay, but then there's an interesting observation that while for the bosons, we again get a two-dimensional hyperbolic space here. So this is again an ADS2 metric if you want. For the fermions, we get a two-sphere. Okay, and again, this difference is related to the fact that there's a symmetry of the density matrices for these states. In one case, this is just an SU2 matrix, whereas in the other, it's SU2, so with the symmetries of a hyperbolic space. Okay, and I just wanted to point out that this is one example I know where the metric is not an ADS metric, but it's something else. It's a two-dimensional sphere. Okay, this is just an interesting observation, and again, this brings me to my point. It would be very nice to be able to associate some dynamics to this other example of having a different geometry, different from ADS. But of course, this is still a question for the future, but I think it's an interesting one in the context of dualities. Okay, so let me just very briefly mention that already a few years ago now with Schuwig and Divayotti, we had some analysis of Fisher information on the gravity side. And so again, this is related to this Buell distance or divergent that I just introduced with calling F now. So let me go back. F is this expression here. Okay. And then the Fisher metric is again obtained by taking derivatives with respect to the coupling of this fidelity. And so what people did already some years back is to consider couplings dual to deformations of the ADS metric. And so this was just done by Tadashi Takayanagi and collaborators in 2015. And they considered pure states and marginal couplings. So pure states means that really they have this scenario here, where then essentially this reduces to a 2-point function. And they were able to compare on the field theory and the gravity side. And on the gravity side, they made this proposal here. So this is the Newton constant, some numerical factor, and this is the volume of the entangling region at the boundary. And for the pure states, actually, there's some regularization required, but this is also true for the field theory side. And so they were able to match this to something in the field theory, also the equivalent expression on the field theory side. So in this paper, we made a proposal for mixed states for this fidelity, where we just proposed this finite expression. So mixed states require a finite fidelity, where we take a difference between the volume of a state of a space which is deformed by some relevant or metric perturbations. And then for the finiteness, we subtract the result for the standard ADS geometry. And so in that case, for this M being a metric or relevant scalar deformation, this result has the expected scaling behavior, the size of the entangling region again. So this is, if it's a spherical region, it will give out to the 2 delta, with delta the dimension of this deformation. So for the metric, this will be D again. Okay, so this is already some years back. So there's some ideas of making a very simple proposal for this fidelity on the gravity side, which is essentially just the volume. For those of you who are familiar with complexities, this might ring a bell. Okay, so now I used up already quite a lot of my time, but let me just very briefly mention the 2 other things I wanted to show to you, but I will really make sure to finish at 10:50. So the second point I wanted to show to you, again, in this motivation which I laid out at the beginning, is the concept of the modular Hamiltonian and modular flow. Okay, again here, as for the Buell metric, the state, we start with a state given by some density matrix, and we consider some entangling region, which is called V. And then, of course, we have the standard expression for the entanglement entropy that you see here. And so now the modular Hamiltonian is defined as a generalized Hamiltonian, which is defined implicitly via this equation. So essentially, to this reduced density matrix, you write it in such a form which is well known from statistical mechanics. And this defines implicitly this Hamiltonian here, which is referred to as the modular Hamiltonian. So really, this presents some generalized time evolution, or if you want also Euclidean time evolution, where this time now, of course, has a different interpretation depending on which kind of matrix you actually started with. And so this concept has many applications in many body physics and also in quantum field theory, also again, for instance, to detect topological order. There's again relations to the relative entropy, as we already discussed before. And in ADS CFT, this has been used a lot for bulk reconstruction from CFT boundary data. So this is this program related to what I'm explaining to you this morning. And you start with the information contained in the QFT boundary data and use it to reconstruct the structure of your gravity fields in the ADS bulk. Okay, so now it's interesting that this modular Hamiltonian is known explicitly only in a very small number of cases. And this was studied already a long time ago in the context of algebraic quantum field theory. And the most famous, well-known example where there's an explicit result is the example of a QFT on Rindler spacetime. So this is Rindler spacetime depicted here. So, so essentially, this corresponds to an accelerated reference frame in Minkowski spacetime. So you consider observers moving along these lines here. And so there's a famous result by Visignano and Wichmann, and it's from algebraic quantum field theory, so it's referred to as the Visignano and Wichmann theorem, that in this case, the modular Hamiltonian with some regularization can be computed explicitly, and it's local, and given by the expression here involving the time component of the energy momentum tensor. So this is the most well-known example and also has been studied also in the context of ADS-CFT to relate this to structures on the gravity side. Further examples that are well explicitly known is the CFT vacuum on a ball, then in 2 dimensions, if there's a single interval, and then there's also the vacuum state on the cylinder or the thermal state on the real line. So these are examples where calculations are known.
I have a question.
Yeah.
Is it known, or is there any understanding of in which cases the modular Hamiltonian is local? Because in general it is not. In this case it is.
Excellent question. So this was just the point of the paper we wrote, and I would like to show to you. So, okay, in general, the model is not local. Okay, I think in general there's no, kind of sufficient and necessary condition to say under these conditions we have a modular Hamiltonian. So what I'm going to show you now is that actually we found some examples where it is actually non-local, but nevertheless we managed to calculate the modular flow. So that was the new idea of our paper.
But is there some, I mean, maybe you're going to say, but is intuition or for when you might expect it to be local?
Okay, let me show my next 3 slides.
Okay, sorry, yeah.
Okay, maybe let me first define what the modular flow is. So the modular flow is the flow generated by the modular Hamiltonian. So it corresponds to a generalized time evolution with this reduced density matrix that I defined. So the modular flow is called sigma, and it's just this time evolution. So you can define the flow by a particular operator. And so the modular Hamiltonian enters this flow. Okay, so the upshot, I'm heading towards answering Roberta's question. So we had this paper this summer, and there we looked at free fermions in 1 + 1 dimensions. And we considered an entangling region which corresponds of n disjoint intervals. And essentially, what our very excellent students in postdoc found is that you can actually calculate this modular flows in terms of the reduced propagator without having to evaluate the modular Hamiltonian. And then actually there's a pole structure of this modular flow which you can investigate and draw some conclusions. But okay, so the essential point is if we for free fermions in 1 + 1 dimensions, we calculated the modular flow for just a fermionic field here. And the upshot is that this will be given by this integral with a particular smearing function, but the smearing function is related to this propagator reduced to the entangling region. Okay, so that's the upshot of this paper, but then the further upshot is that this allows us to study the locality properties. Okay, so I was going to tell you a little bit about this Tomita and Takizaki modular theory, but I think in view of the time, I'm going to skip it. It just essentially just to say that this is quite firmly rooted in this algebraic quantum field theory already from some time ago. I recommend this paper where there's a nice review.
Johanna?
Yeah?
Just wanted to say that you have about 5 minutes.
Yes, thank you. Yes, thanks for warning. Okay. Then there's another concept which we can define, which is the so-called modular two-point function. So that's the two-point function for a state in a Hilbert space, where, okay, here you see this modular flow appearing, and then it's defined in a strip on the both sides of the real line. And so in this region, you have this order, and in that region, you have that order. And then just writing the modular flow with a particular test function, then using results from this Tomita-Takizaki theory, one can actually show that this contribution here gives you a combination of this modular two-point function. And so really the pole structure of this modular flow will be related to the pole structure of this modular two-point function. Okay, so here comes my discussion of locality. So that's what Roberto was asking about. So we compute the free fermion modular flow for a number of examples. on the plane and cylinder, so with bound antisymmetric and symmetric boundary conditions, and on the torus. And so in this approach that we present, we can actually discuss locality. So, so non-local means that the kernel in this modular flow is a smooth function of all of this entangling region. And then now this reduces, then this reduces to something called, which we call bilocal, where actually this reduces to a delta function. And then there's only a discrete set of contributions, and still this flow then couples pairs of distinct points. And local means that at time t equals to 0, actually these 2 points have to coincide. And the locality properties depend on the boundary conditions and the temperature. So again, I should say there were some other people, for instance, Gabriel Wong and Diana Varman in the States. They calculated this already for some examples, but we added some more where this non-locality appears. And so this locality properties are reflected in the structure of the poles and cuts in the modular 2-point function. So there's this relation between this 2-point function and the modular flow. Okay, so Roberto, I don't think I can go into all the details, but if you're interested, please have a look at this paper. So actually we can scan through various regions. So if you start at high temperatures, then we have thermal and local behavior of this modular flow. And then when we lower the temperature, the modular flow adds these bilocal couplings between an infinite discrete set of points. And so this can be traced back to the antiperiodicity of the thermal propagator. And okay, now I didn't tell you what the KMS condition is for lack of time. So if you're interested, please have a look at the paper. And then when the temperature goes to 0, then we actually obtain a branch cut. So let me very quickly show you the poles in the complex time plane. So for the plane, there's so the poles of this modular 2-point function in the plane, there's just these dots. But then if you have a cylinder in the space-like direction, with periodic boundary conditions, so that's P means periodic, then these become branch cuts. And on the torus, you get such a structure, and this means now if you go to high temperatures, you get this behavior in the plane, but if you go to low temperatures, these actually become branch cuts, and so this reproduces the result for the cylinder when the temperature goes to 0. Okay, now in the last 1 minute, let me just very briefly mention the third topic I was going to allude to, so which also needs to be mentioned in this context, which is this idea of circuit complexity. So what is complexity? Well, you consider a set of predefined unitary transformations in the Hilbert space, and the question is how many of these need to be applied to reach any given state from a reference state. So again, this is a concept from information theory. And okay, so here there's a formula for what I just told you. So how many, so these predefined states are called gates. How many states do I have to apply to this reference state to get to a final state? So it's really a question which arises in quantum computing, and complexity tells us how complex a particular calculation is for a quantum computer. Now, there were some proposals for this on the gravity side. Now, so then the idea is, of course, this again is again defined only for finite dimensional Hilbert spaces, and the idea is can we define a similar concept for infinite Hilbert spaces. And most of the progress so far was for free field theories, and so more recently, okay. Let me skip this. Let me just tell you the motivation for studying this in context of ADS-CFT are these proposals by Susskind, where he actually studies properties of black holes in anti-de Sitter spacetime using this complexity notion. And so he has two different proposals, and so far it's not really clear which of them is the good one, or if we need even more complicated ones. But that provides a lot of motivation to include this concept of complexity in quantum field theory. Now, the problem, of course, in quantum field theory is that everything is continuous. And so if we want to, we have to define a set of gates, and we have to define these reference states, and I mean there's actually too many choices, and in some sense, and so we have to find some rules to do something useful. So so we have to determine a set of gates, and we have to pick examples for reference states, which could be spatially unentangled states, the highest weight state in a symmetry multiplet. These are just examples. And then one defines a so-called cost function, which determines the expense of applying a particular gate. Okay. So in the last 30 seconds, let me just say very quickly that there was a lot of progress on studying this for conformal field theories, following by this work by Saputo and Magam. And so they actually suggested defining gates from conformal transformations, and the reference state being then a primary state. So then there's transformations in a particular Verma module. Okay, and there were various refinements, so I think in view of time, I won't have time to explain them. So with my students, we found a nice relation to the geometric group action on co-adjoint orbits, and we extended previous results also to Kac-Moody algebras. Nevertheless, I think this whole approach is still somewhat restricted. So if you are interested, we can talk about it later. And I would also like to mention this follow-up work by Mario Flori, my former student who is now a postdoc in Madrid, together with Michael Heller. And they, again, use the fidelity susceptibility, also called Fubini-Studi metric in this context, and found optimal circuits which are determined by the so-called Euler and Arnold equations of classical mechanics. So just to say that there are still many other interesting things that you can do, and let me just very quickly finish. So I showed you that inspired by gauge-gravity duality, there are many beautiful new connections between quantum field theory and geometry. And so a very important ingredient here is information theory. And as I showed you, there are many interesting examples of what can already be done. So, but I think the motivation really to do this is this big challenge to understand the working mechanism of gauge-gravity duality in general. And so, as I mentioned, I was going to come back to this. I mean, what is really missing is to understand how the dynamics, which is so beautifully present in the original ADS-CFT correspondence of Maldacena, emerges in this more general context. And so I hope many people will be interested in looking at this question mark here. Okay, sorry for going over time, and so I'm done now. Thanks.
It's okay. Thank you, Johanna, for this very nice introduction. So are there questions? I hear sounds from Santiago. Are there questions?
Well, maybe it's a curiosity. So, Johanna, if I understood well, this Fisher metric is just inducing from your Hilbert space a distance in the space of parameters.
Yes.
So it's basically so typically, since your Hilbert space scalar product is complex, usually this is one of the things you can do to induce this Hermitian object, which is this Fubini-Studi metric or Fisher metric. But you can also induce an anti-Hermitian object, which is what people call the Berry curvature.
Yes, exactly.
From there, you can obtain very interesting things like quantized things like cloudless pumping and I don't know. So does this make?
Okay, sorry. Yes, it's very important, and thanks for mentioning it. I'm sorry, for reason of time, I didn't include it, so I should come back to this. So this Fubini-Studi metric is really a metric, a kind of Kähler metric, if you want. And as Javier just explained, on one hand side, it gives you a real metric, but on the other hand, it gives you also an antisymmetric tensor, which then gives rise to the so-called Berry phase. And so this Berry phase actually makes a lot of appearances in these papers as well. So so I didn't explain the details, but this is certainly very interesting. And another very interesting paper is one from 2019 by Czech, Lamprou, De Boer, and G, I think, where they relate this Berry phase to the curvature in the anti-de Sitter space. Okay, so there again, I mean, there are some caveats, and it really works again because it's anti-de Sitter space, and there's again this locality which I mentioned there. Also, the modular flow plays a role there. Okay, so the short answer is this is a very important remark, and unfortunately, I didn't have time to talk about this, but this very curvature which arises here from this antisymmetric imaginary part, essentially of the scalar metric, also plays a very important role in this context, and it's already been investigated, but I think there's many more interesting things which can be done with it.
Yeah, thank you.
Okay, more questions?
Well, there were already quite a lot of questions.
Somebody was asking.
Did I answer your question about the locality?
Yeah, at least I got an idea. I think I will go to your paper to see in more detail.
Yeah, I'm sorry, it was a bit quick.
No, it's okay, but I understand that it's a complicated question. But yeah, thank you.
So if I may ask, probably you went a little fast through the fermion modular calculations. So this analytic structure of the modular propagator, what is the physical interpretation of these poles? I mean, what information are they giving me?
Yeah, okay, so our idea was to find new examples of explicitly calculating the modular flow. So as I mentioned, the one example which is very well known is the one for the Rinder space. Okay, so this has been known for a very long time. And okay, I didn't have time to explain, but in this free fermion case, some of the plane and the torus, they were already known for some while. And so the idea here now was to use a particular resolvent method for this kernel. So the resolvent is written here. To be able to evaluate this flow without having to evaluate the modular Hamiltonian itself. Okay. And so then the physical statement is that, okay, but nevertheless, of course, you can see that this is precisely for free fermions, and this propagator will be the free fermion propagator in 1+1 dimensions. And so the statement of this paper is that we find new examples where the modular flow is non-local, okay, in the sense that it couples operators from different points. And but this non-locality happens only in very specific cases. And so in particular, okay, so we have a lot of examples of this bilocality, but the non-locality only happens if you have a cylinder where you have a periodic boundary condition in the space direction. I mean, of course, you have an anti-periodic boundary in the time if you have a torus, but here, if we have a periodic boundary in the space direction on the cylinder, then there, okay, so this modular two-point function gets actually a branch cut. So you get these branch cuts. So this is the pole structure in this modular two-point function.
You're saying the type of analytic structure tells me patterns of non-locality or different characters?
Exactly. Yes, precisely. That's exactly what I want to say. So if this thing has these branch cuts, then this is the modular flow will be non-local, and it couples information from different points in space, okay, in different entangling intervals. And so the upshot is that we can trace back the non-locality of this modular flow to the analytic structure of this propagator.
Okay.
So, and this means we found an example, which is the cylinder with periodic boundary conditions, where you really have this non-local structure, but nevertheless you can explicitly calculate the modular flow. So in that sense, it's a new example. And of course, yeah, it would be interesting. I mean, one could do this for other operators. Here we just did it for the very simplest case, but maybe we could do it for some composite operators, maybe higher spin operators, or also, and then bring us closer to ABS-CFT.
Okay, so if there are no more questions, I would like to thank Johanna again. I'm going to clap
Yeah, thank
for
you for listening.
Thank you very much.